All right, today we're doing something really cool. We're going to connect the tiniest thing imaginable, the quantum world of an atom, with the absolute vastness of space. And we'll see how scientists use, well, just light to unlock the secrets hidden inside matter itself.
I mean, think about it for a second. It seems like a totally impossible question, right? We obviously can't just fly out to a star and grab a sample. There are millions, sometimes billions, of light years away. So, how in the world do we have any clue what they're actually made of?
Well, the answer is it's beautiful, really. We read the light. That's it. Turns out every single element in the universe, doesn't matter if it's in a lab here on Earth or in some super distant star, leaves behind a unique fingerprint in the light it gives off. All we have to do is learn how to read those fingerprints.
Okay, so let's get into it. Before we can read those cosmic fingerprints, we've got to understand the kind of weird but super strict rules that run things inside an atom. So, yeah, welcome to the quantum world.
This is really the heart of quantum mechanics right here. An electron zipping around an atom can't just have any old amount of energy. It's stuck on specific, discrete energy levels. The best way to picture it is like a ladder. You can stand on the first step or the second step, but you can't just float in between the steps. It's one or the other. So let's get the rules for this energy ladder straight. Rule 1, like we said, no in-betweens. Rule 2 is a little weird. You'll notice the energy values are all negative. Why? Well, think of it like an energy debt. The electron is stuck to the atom. You have to give it energy to pull it away and get it up to zero energy where it's finally free. So that lowest step, the one with the biggest negative number, that's its most stable spot. We call that the ground state. Any step higher up is what we call an excited state.
So, how does an electron actually jump up and down this ladder? It's all about light particles, photons. To jump up to a higher step, an electron has to absorb a photon that has the perfect, exact amount of energy for that jump. Not too much, not too little, and to fall back down, it spits out a photon with that exact same energy. Seriously, this one idea is the key to everything we're about to talk about. And this whole process, this absorbing and spitting out of photons, this is what creates those fingerprints we're hunting for. And they show up in 3 different ways, which we call spectra.
First up, we've got the continuous spectrum. Just picture white light coming from something really hot and dense, like the filament in an old-school light bulb, or even the core of a star. If you shine that light through a prism, you get what you'd expect, a beautiful, complete, unbroken rainbow. Every single color is there, no gaps at all. This is our starting point, our baseline. Okay, but things get really interesting when you put some gas in the way. Take a look. On the left, that's an emission spectrum. See those bright, colorful lines on a totally black background? Now look at the right. That's an absorption spectrum. It's a full rainbow, but with these dark lines cutting through it. Do you see it? They are perfect opposites. The dark lines on the right are in the exact same spots as the bright lines on the left. That's not a coincidence.
So what is going on? Well, the emission spectrum, the bright lines, that comes from a hot, glowing gas. Its electrons are all energized, they're excited, and as they fall back down their energy ladders, they emit those specific photons, creating the bright lines. The absorption spectrum is the opposite story. That happens when you shine a full rainbow of light through a cloud of cooler gas. The electrons in that cool gas see all the light passing by, and they absorb only the photons with the exact energies they need to jump up their ladders. They literally pluck those specific colors out of the rainbow, leaving behind those dark gaps.
So okay, we can see these fingerprints. That's cool. But here's the really powerful part. We can actually turn these lines into hard numbers. The energy of every single photon is directly tied to specific wavelength or frequency of light. And guess what? We can calculate it.
All right, let's run through an example to see exactly how this works. We've got an electron, and it's falling from a high energy level down to a lower one. That means it's going to spit out a photon. Our mission is to figure out the exact wavelength of that photon.
The process is actually pretty straightforward. Step 1. Just find the difference in energy between the 2 levels. Simple subtraction. Then we use this handy little formula that connects energy to wavelength. It uses a couple of famous numbers from physics, Planck's constant and the speed of light. All we have to do is plug everything in.
And boom, out pops our answer, 121 nanometers. Now, that's a wavelength in the ultraviolet part of the spectrum, so we can't see it with our eyes. But to an astronomer's telescope, that is a crystal clear signal that tells them exactly what just happened inside that atom, trillions of miles away. Okay, you'll see physicists use a different unit a lot for these super tiny energies. Instead of joules, they use something called an electron volt, or just EV.
It just makes the numbers easier to work with. So let's try another problem, but this time using EV.
The process is basically identical. First, find the energy difference. But wait, there's one extra really important step here. We have to convert our answer from EV back into joules before we can use our formula. Once you do that, though, it's the exact same calculation we just did.
And what do we get? 488 nanometers. That's a color we can see. It's a nice cyan blue light. So you can see how powerful this is. If we're looking at a distant nebula and we see a bright line at exactly 488 nanometers, we know for a fact that this specific energy jump is happening in those atoms.
Okay, cool. We can also flip this whole thing around. What if an electron absorbs a photon to jump up the ladder? And just to mix things up, let's calculate the light's frequency this time, instead of its wavelength.
Once again, the first few steps are exactly the same. Find the energy difference in EV, then convert that to joules. But now, since we're looking for frequency, we use a slightly different but related formula. E equals h times f. We just rearrange that to solve for f, the frequency.
And that gives us our answer, 3.18 times 10 to the 15th hertz. That makes sense, right? It was a really big energy jump for the electron, so it needed a really high-frequency photon to make it happen.
All right, for our last problem, let's go for the ultimate jump. What does it take to not just bump an electron up a level, but to hit it so hard it gets knocked clean out of the atom altogether? This process has a cool name, photoionization. Remember how we said a free electron has an energy of 0? Well, a hydrogen atom in its ground state is at negative 13.6 eV. So to free it, we need to give it exactly 13.6 EVs of energy to get it up to 0. We take that energy, convert it to joules, and plug it into our wavelength formula one last time.
And the answer we get is 91.3 nanometers. Now, this is a really important number in astronomy. Any photon with this wavelength, or an even shorter, more energetic wavelength, has enough punch to completely ionize a hydrogen atom.
Okay, let's step back from the calculator for a minute and bring this all back home. How does all this math help us figure out what stars are made of?
This is where it all clicks into place. The fact that we see these sharp, distinct lines at all, instead of just a blurry mess, is solid proof that these energy levels are real, that they're quantized. The bright emission lines, they tell us what a hot, glowing cloud of gas is made of. And the dark absorption lines we see in starlight, they tell us what's in the star's cooler outer atmosphere, because those are the elements that are absorbing the light from the hot core. Every element, hydrogen, helium, iron, you name it, has its own unique, unmistakable barcode of lines.
This quote just nails it. A star's core pumps out a perfect continuous rainbow of light. But as that light travels through the star's own atmosphere, the elements floating around in there act like filters, each one absorbing its own signature wavelengths. So by the time that light reaches us here on Earth, what we see is the original rainbow with a bunch of very specific colors missing. We are literally seeing the chemical shadow cast by the star's atmosphere.
So by learning to read the fingerprint of a single atom, we can figure out the chemistry of a star that's impossibly far away. And that just leaves you with this one kind of mind-blown thought. If we can learn all this from just one atom's light, what kind of story is being told in the combined light of billions of stars in an entire galaxy? That's the incredible power of this stuff. Thanks for tuning in.